So we have learned how to do derivatives of algebraic functions, and we have learned how to do derivatives of trig functions, and now it's time to move into the exponential function category. So we're going to call f of x, and we're just going to give it some arbitrary base b to the x as an exponential function. Now, if you've worked with exponential functions before, then you know that b is always bigger than 0, it's always positive base, and b is usually not 1 because 1 to any power is not really an exponential function. So we have a positive base b, and okay, so this is just kind of the definition of what an exponential function is. So we're going to have to fall back, at least to kind of show you why the derivative is what it is. We're going to fall back on our limit definition. So f prime of x is equal to, we're going to do the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so we're going to use f of x equals b to the x. We're just going to use a base b because then it'll generalize for any base. Okay, so this will be f prime of x is now equal to the limit as h approaches 0. So this will be f of x plus h, means I'm going to put an x plus h in for x. So this is b to the x plus h, and then minus the original f, which is just b to the x, all over h. Okay, so now when I write this b to the x plus h, right, if I had b squared times b squared, I could write that as b to the 2 plus 2, okay? So essentially what I'm going to do is unadd them. So I'm going to rewrite this instead as the limit as h approaches 0 of b to the x times b to the h. Because when I have the same base and I'm multiplying them, it's really like adding them. Minus b to the x over h. Now I did that so that you can see that b to the x is common to both of these, right? So I'm going to factor out b to the x on the top. So this will be equal to the limit as h approaches 0 of b to the x, factoring it out, b to the h, and then I'll have minus 1 here over h. Now, my limit here is as h approaches 0. This b to the x, right, it doesn't have any bearing on h, so I can actually pull the b to the x out front, right? So now we have f prime of x equals b to the x times the limit as h approaches 0 of b to the h minus 1 over h. Okay, so basically we're going to have, I'm going to show you how we kind of come up with this. It's a little simpler than this, but I want to show you how it works. But so f prime of an exponential function will be b to the x, and then, I don't know, we'll just call this times m of x, okay? So we're going to just call this function, and we're just going to kind of call it a function, and we're just going to call it m, okay? So we're going to explore what m is. I'm going to switch over to my computer screen. We're switching over to the computer screen, and so here is my m of x, right? We called it b to the x times m of x. And now Desmos doesn't like h, so I had to use x. So this is basically 1/2 to the x minus 1 over x. So I changed the base b to 1/2 for right now. And I know that we've done a lab that said that tables are not a good way to find a limit. Like this is the easiest way for me to kind of show you what this is. So as I change my b, I'm going to get a different number. So we're going to plot a few points on what will be this m of x, okay? So if I look at the limit as x approaches 0 of 1/2 to the x minus 1, that means I'm going to plot a point on my derivative. So when b is 1/2, okay, so let's check out, let's look at closely here. So right, I definitely look like I have a limit here, and this m over here looks like it agrees to negative 0.693. Actually 1, we'll just go 3 decimals so just to make it easier for me. So that's negative 0.693. Okay, let's take that graph off. We don't really need it there. We just want to use the table. So there's our first point, okay? So let's get a little bigger. Now I know my b can't be zeros, right? So all of my my graph will remain on this side. So because of the limitations of exponential functions. So let's go a little bit bigger than a half. Well, let's try 3/4 to the x, okay? And so my new table populated. And so when b is 3/4, it looks to me like if I look here, right, I agree to 3 decimal points to negative 0.287. So we'll put that point on. Oh, I got to put a comma between them. Desmos is so picky. Okay, so there's our first 2 points. Okay, so let's get a little bit bigger than 3/4. Okay. So let's put in 5/4. Okay, so if I plug in 5/4, then it looks like my output here at 5/4, my m of x is approximately 0.223, right? It agrees to there. Oops, that's a decimal, not a comma. 0.223. And there's my next point, okay? So let's get a little bigger here. We'll just go to 2. How's that? So if we put in, oops, I put in 3. I put in 2 here, and it looks like the limit as really h is approaching 0 here is, from our table, 0.693. So when b is 2, my y value, probably need parentheses, 2 comma 0.693. We'll make these the same color. Okay. All right, so I have a few points. So let's get bigger now. Let's go to, how about 4? Okay, so when b is 4, the limit is h approaches 0 from my table is 1.386. Okay, so that's our next point. At when b is 4, I get out 1.386. And I forgot my comma again between those. There we go. There's my point. Okay. So let me do one more bigger. So let's go to like, so we'll go up 8, actually. I lost my exponent now. Okay, so 8, when my base is 8, it looks like my table is telling me my y value is approaching 2.079. Okay, so I'm going to plot that point. Oops, forgot a comma again. Desmos is so picky. There we go. Okay, so let me plot one more that's just a little bit closer to 0. So let's say I go to, we'll just do like 1/10. That's very close, okay? So when x is a 10th, let's see, what am I going to find? Oops, I got that one wrong. There we go. So it looks like my limit table is telling me that it's approaching negative 2.302. All right. Now, so this may look familiar to you or may not. Now, I'm missing a lot of gaps, but I know that this will not be, right, it's not going to cross over the y-axis here because that would mean that my b would be 0. And I know that an exponential function doesn't work like that. So I know that my graph is going to stay over here. Now it looks like my graph is plunging down here, and then it looks like it's kind of like rising sort of slowly up here, okay? So maybe if you're familiar with different graphs, maybe you recognize it. It sort of looks kind of like the square root of x a little bit shifted downward, but square root of x starts here at 0, right? And it doesn't have this sort of tail that's coming down. This actually is the graph of y equals, now watch how this fills in here. It's the graph of the natural log of x. Oh, I must have something wrong here. What happened to my 8? Actually, let's put 8 back in here because I missed it. Let's see. Obviously, I did something wrong. 8 to the x. It should, oh, I missed a 0, 2.079, that's why. And there, it fit right on my line. So essentially, right, when I do this limit of b to the x minus 1, b to the h minus 1 over h, what I end up getting is the natural log function. So what that means is that when I do this, right, I found out that my derivative of an exponential function was b to the x times m of x. Well, we just found out that m of x is actually the natural log of x. So our real derivative then is basically b to the x times the natural log of b. Okay, so at 2, right, this is the natural log of 2, right? When my base is 2, then this m of x is equal to the natural log of 2. And when my m of x is, or my b is 4, then my point here says that the m of x at when my base is 4 is the natural log of 4, which is 1.386. Okay, now I've got them, right, I've got them a little bit approximated because they probably go on further than that. But essentially it follows this pattern. Now the one really nice figure of this is, so if I come down here and look at the natural log of, let's do the natural log of e, right? The natural log of e is just 1. It's somewhere in here. It would be 3, actually 2 point, so there's 3, 2 point, see how it's getting closer to e is about 2.71 something or other, right? So right in there somewhere is 1. So when I get the natural log of e, it is actually 1. So that's really nice when we do the derivatives of e to the x, because basically we have the derivative would be e to the x times ln e, but ln e is just 1. So we love e to the x. Okay, so let's return back to some problems. Okay, so returning then back to some examples, we were doing the f prime of x equals b to the x times m of x, and we found from the tables actually work in this case, that f prime of x is actually b to the x times the natural log of the base, okay? Now the really great thing is that we mostly use e. Occasionally other bases come up, but we mostly use e. And e is great because if I do the derivative of, if f, let's say, is e to the x, then that means I have the derivative will be e to the x itself, right, times ln e, and ln e is just 1, right? Actually, that's not an equal. So that means that f prime of x is just e to the x. So the derivative of e to the x is just e to the x, which is lovely, okay? Now we can also, oh, I've already done that. So the chain rule then here, if I have e to a power, then my chain rule says, right, so the derivative of e to the x is e to the x, so it will be e to the g of x, right? And then using the chain rule means I'm going to multiply it by the derivative of the exponent. So it's e to the g of x times g prime of x if I'm doing the derivative of e to something that's not just x, okay? And even, actually we can kind of even think of it as e to the x because the derivative of x is still 1, okay? All right, so let's do some mixing of rules here, okay? So I have e to the cosine of x, okay? So that means if I do the derivative, f prime of x will be, and I'm in e, so I'll have e to the cosine of x, right? It's always e to the x, or e to the whatever power it is, that's always there, then times the derivative of the exponent. In this case, that would be negative sine of x. So maybe I would write it as negative sine of x e to the cosine of x, just for neatness sake. There's my f prime of x. Okay, so we have y equals e to the x squared over 3x. So this is a quotient rule problem, right? So my y prime will be, it's the bottom, 3x, times the derivative of the top. The derivative of e to the x squared will be e to that power again, then times the derivative of the power, so times 2x. And then minus, then I'm going to have e to the x squared times the derivative of 3x, which is 3, all over. Then when I square 3x, I get 9x squared. Okay, so I have x times e to the 2x. So this one requires the product rule. So f prime of x is equal to, I'll do the derivative of x first just because it's first. So that's 1 times e to the 2x plus then x times the derivative of e to the 2x. So the derivative of anything, of e to any power is always e to that same power, then times the derivative of the power, which is 2. And that's it. I mean, I could neaten this up a little bit and just call this e to the 2x plus 2x e to the 2x is f prime of x equals. Now, maybe your book will show that maybe you factor out the e to the 2x. It's really not necessary unless we're doing something specific with it. All right, so these do show up every once in a while, but I have a 2 to the x this time, an exponential function. I can tell because the power is the exponent. That's how I can tell my exponential functions, right? These don't, I know lots of students want to confuse these with x to this, like x squared, right? So the difference when I use this 2x, right, the n times x to the n minus 1, the number is the power, x is the base. Here we have the number is the base, x is the power. So these are completely different rules. All right, so I'm going to use the quotient rule again. So f prime of x is the bottom times the derivative of the top. So that means I have x plus 1 bottom times the derivative of the top. So it's always that same exponential function. And now in this case, because I don't have e to the x, because the natural log of e is 1, so we don't write it, the natural log of 2 is not 1, so we do have to write it. So it's the natural times the natural log of 2, and then minus 2 to the x times the derivative of x plus 1, which is just 1, so I won't write that. In the bottom, I have x plus 1 quantity squared. Okay? And so let me just do one more just as a, so if f of x equals, let's see, what if I have 2 to the x, actually that's not 2 to the x, I have 2 to the x over the natural log of 2, okay? I did this one because I want to make sure that you understand that the natural log of 2 is just a number. It looks weird, but it's just a number that we can put in our calculator. So we can really think of ln2 as a constant. So we can think of this as 1 over the natural log of 2 times 2 to the x. And then this is our constant multiplier, right? If we have, like, just like if we have, if we have 3x squared, right? Then our derivative here was just 3 times 2x. Like the 3 just sits there and gets multiplied by the derivative of x squared. So this is the same thing here. So this would be just my f prime of x would just be 1 over ln2 because it's just a constant. And then the derivative of 2 to the x would be 2 to the x times ln2. And I chose my constant so perfectly that these actually cancel out in this particular case and just leave me with 2 to the x. So just remember the natural log of a number is just a constant, right? It's an irrational constant, but it's still a constant. We will pick up with derivatives of logs next.